Hello. Today we're going to expand our understanding of the types of angles that can interact with circles. What you see on the screen in front of you is a reminder of something that we proved a couple of days ago, which is the inscribed angle theorem, which basically says that if I have an inscribed angle in a circle, its measure equals 1/2 the measure of the intercepted arc. So in this case, I'm comparing this arc right here to this angle. And I can write it in the form that I have in the yellow box here that says that the measure of angle A is 1/2 of the measure of the intercepted arc, or if it's more convenient algebraically, I could say that 2 times the measure of angle A equals the measure of the intercepted arc. Algebraically the same. But today we're going to look at what happens when we have different kinds of measures. So let me just call something up here for you. Hey, look, I have here a new type of angle. And this angle is what we call a tangent chord angle. And let's look at how this is similar to the inscribed angle. They're similar in one key fashion, and that is this. The vertex of this angle is on the circle, just like it is here. And that's going to give us one reason to believe the statement that I'm putting a yellow box around right now, which is that the measure of this tangent chord angle that I'm calling angle X is 1/2 the measure of the intercepted arc, which in this case is this arc right here, XY. So in this case, the arc is intercepted by the vertex and the other part of the chord. Whereas over in this one, this arc is intercepted by 2 ends of 2 different chords. But note the similarities in their measures. So the connection I want you to see here is that both of these angles have their vertex on the circle, and that means that the relationship between those angles and the intercepted arcs are the same. They're 1/2 the size. So we proved this condition over on the left a couple of days ago. Now what I want to do is I want to prove the condition over on the right. The good news is that this is a little bit easier than the inscribed angle proof. And I'm not going to do a formal proof here, but I am going to try and write this down in a way that you can follow and you can understand my logic. And then if you have questions, of course, you can ask when we have class tomorrow. So the first thing is I have here a tangent chord angle that is intercepting arc XY. And what I want to do first, I'm just going to change what I've written here a little bit because I want to be very clear about which angles I'm working with, and I'm about to make a whole bunch of angles around X. So rather than call it X, I'm going to say that the measure of angle YXZ is equal to 1/2 of that arc XY. Okay, so as is frequently the case, it is a good idea in this case to draw 2 radii, because I can always draw radii between points or segments between points. And then I know because they're radii, they are congruent. So I know that I have OX congruent to OY because they are radii. Now, I'm not writing the full reason here. I'm just taking notes about where I've already gone so far. Before I continue, there's one other thing I want to do. I want to go ahead and just say that the measure of angle XY is equal to 2A. I'm going to use A instead of X to keep from getting too confused about points and measures and algebra and all of that stuff. I'm just going to declare that as the measure. It's 2a. This is a common technique that we've done before. I'm choosing to name it as 2a because then I can hopefully avoid dealing with fractions in my algebra later on. All right, so let's take a look at what we've created here. The first thing I noticed that I've created is that I've created an isosceles triangle OXY. And because it's isosceles, that means that angle OXY and angle OYX are congruent. Because if it's an angry triangle, then it's a blushing triangle. Okay, so I know that this and this are the same. So let's take a look at the measure of angle O for just a moment. The measure of angle O has two things going for it. The first one is that it is equal to the measure of the arc that it's intercepting. So it's equal to the measure of arc XY. The other thing I know about it is that it's equal to 180 degrees minus twice the measure of angle YXO, or I've been calling it OXY, so let's keep doing that, OXY. Do you see why that's true? Because if I subtract this angle and this angle from 180, I get the central angle, but the two angles I just marked are the same. So it's the same as doubling one of them. So let's do a little bit of algebra with this second statement for a moment. So I'm going to suggest that, oops, I lost my O, measure of angle O. All right, so now I'm going to subtract 180 from both sides. Okay, cool. So I'm going to get the measure of angle O minus 180 equals negative 2 times the measure of OXY. All right. And then I'm going to divide both sides by negative 2. And when I divide this by negative 2 over here, it's going to turn that into a positive 180 minus the measure of angle O over 2. So that step to there is just acknowledging that the negative sign could be moved up to the numerator, and then I could redistribute my parts. Take a minute to pause and make sure you understand why those two expressions connected by the arrows there are the same. And then over on the right-hand side, I have just the measure of angle OXY. Okay, but I've already said I have something here that could go there. So this means that I get 180 minus 2a over 2. Okay, but then I can divide on the left and get 90 minus a equals the measure of OXY. All right, so that's cool. That feels important. But you're probably now screaming at the screen and saying, but Mr. Leach, that's not the angle we want. We want the other angle that's around x. We want YXZ. You're not wrong. But now here's where the fun part comes in. You may recall from yesterday that we proved that a radius intersects a tangent to the circle at right angles. So I know that the measure of angle OXZ is 90 degrees. Well, the measure of angle OXZ is just equal to the measure of angle OXY plus the measure of angle YXZ. So now let's do some replacing. I know this is 90. And I know that OXY is 90 minus A. So now, if I subtract 90 from both sides, I get 0 equals negative a plus the measure of angle y x z. If I add a to both sides, then I get a equals the measure of angle y x z. Hey, look, that means that the measure of angle yxz equals 1/2 the measure of xy, because this is 2a. So I've proven it. There it is. The measure of angle yxz is 1/2 the measure of the arc. Hey, smash cut. I've jumped to a new type of angle. So we've looked at angles that have their vertices at the center of our circles, and we've looked at angles that have the vertex on the circle. So now we have a new type of angle that we're going to look at. This time we're going to look at an angle where the vertex is on the interior of the circle, but it's not necessarily the center. These angles are called interior angles because the vertex is on the interior of the circle. They're also, particularly in our book, they're called chord-chord angles because they're formed by the intersection of two chords. Absolutely makes sense, right? Sure it does. Of course it does, Mr. Leash. Everything you always say makes sense. So now we're going to try and prove this. We're going to try and prove that if I want to know the measure of angle FPE in this diagram, then all I have to do is find the measure of this angle, or this arc rather, and this arc, add them together and cut it in half. Easy peasy lemon squeezy. So it's the sum of the arcs that are intercepted by the angle and the vertical angle, and then we cut that in half. Or another way to say it, it's the average of the two angles, or the two arcs that are intercepted by my angles. So let's get to proving it. So the first thing I'm going to do is this. I'm going to do something a little bit counterintuitive. One reason why I would not ask you to do this proof on your own is because the key thing to draw here is not at all obvious. I'm going to draw the chord CF. And in doing so, I'm going to create a situation that I am particularly interested in. Let me clean up this diagram a little bit here. Let's do that and get rid of this. Oh, I didn't want to get rid of the circle. Try that again. Come on. There we go. All right. So when I create this triangle, do you see the triangle that I've just created, CPF? I'm going to go ahead and I'm interested in this angle here that I've labeled 1. I'm interested in this angle here that I've labeled 2. And then my target angle, the angle that I'm interested in for the proof, I'm going to call angle 3. And what I hope you see is that angle 3 in this case is an exterior angle to the triangle that I just created. So since it's an exterior angle, the measure of angle 3 is equal to the sum of the two remote interior angles of that triangle, right? Exterior angle theorem. But here's another thing that I've created with this chord. This angle 1, if you look at it carefully in isolation, this angle 1 is an interior angle that intercepts arc CD. Oops, it turned that into a chord. Dummy. Let's do that again. It captures arc CD. Why would you do that? Right? So the measure of angle 1 can actually be rewritten as 1/2 the measure of arc CD. Likewise, angle 2 is an interior angle that captures FE. So the measure of angle 2 is equal to 1/2 the measure of arc FE. So now if I do a little bit of factoring here, I get this. Hey, look, it's what I was trying to prove. I got the letters in a different order, but that doesn't matter. The measure of angle 3 is half the sum of those two arcs. That proof was pretty straightforward. The hard part of that proof is knowing to draw that line. But everything else from there, if you know what you're looking for, is pretty straightforward. Okay, last section. Another smash cut into the third types of angles that we have talked about. So, to remind you, we've talked about angles where the point of the vertex is somewhere in the circle, where the vertex of the angle is somewhere in the circle. We've looked at what happens when the vertex is on the edge of the circle. Now we're going to look at what happens when the vertex is outside the circle. And all of these are going to have very similar formulas for the same reasons that the other ones did, because the vertex is in the same relative location to the circle, which is to say it's outside. So here and here and here. And as you can see, these come in three different flavors. They come as a secant-secant. So in this case, Vy and Vs are secants. Here, I've got CA as a secant and CD as a tangent. So this is a secant tangent. And then here, I've got two tangents. But in all three cases, the theorem that we're going to work with says this, that the measure of an external angle is half the distance of the measures of the intercepted arc. So you remember in the previous examples where the vertex was inside the circle, the measure of the angle was the half of the sum of the intercepted arcs. Now it's going to be half of the difference of the intercepted arcs. So let's take a look at a secant-secant proof. So if I have a circle here, and let's just quickly draw two secants. And I'm going to label these. Let's call this B, C, A. Just in case we need it, we'll call this circle O. And let's call these 2 points D and E. So what I'm going to try and prove is that the measure of angle A is equal to 1/2 of the measure of BC, that arc, minus the measure of DE. So these are the two intercepted arcs. Do you see them? What I'm going to do is I'm going to, again, draw sort of a non-intuitive segment. This is another reason why I'm not really asking you to do these proofs, because knowing which pieces to add to the picture is not at all obvious here. So I'm going to draw this chord BE. And again, like I did last time, I'm going to number some important angles. I'm going to call this angle 3, and I'm going to call this angle 1. Or no, let's call it angle 2. Don't know why I'm not using 1, but I'm not. Sometimes I'm just crazy that way. All right. So here's what I know. I know that this angle here, this angle 3, once again is the exterior angle of this triangle. Triangle ABE. So do you see it? So in other words, the measure of angle 3 is going to equal the measure of angle 2 plus the measure of angle A, because those are the two remote interior angles to angle 3. Okay, cool. Well, but take a look at a couple of other things. The first one is to note that the measure of angle 3 is also, well, angle 3 is also an inscribed angle. So if I look at this angle here, do you see how it intercepts arc BC? So that means that it is 1/2 the measure of arc BC. Likewise, angle 2 is also an inscribed angle. It is this angle right here, and it intercepts arc DE. So the measure of angle 2 is equal to 1/2 the measure of arc DE. And you can probably already see where this might be headed, but let's finish it off anyway. So now I'm going to replace these two things with these two things. So I'm going to say that 1/2 the measure of BC is equal to 1/2 the measure of DE plus the measure of angle A. Then I'm going to subtract the 1/2 measure of DE from both sides. And that leaves me with 1/2 the measure of BC minus 1/2 the measure of DE equals the measure of angle A. And again, I can factor out the 1/2, and I get what I was looking for. The measure of angle A is equal to 1/2 of the difference of the two intercepted arcs. Now, I'm not going to prove the tangent-tangent or the secant-tangent versions of this because those proofs look fairly similar to the other proofs that we've already done, and I think you've been watching this video long enough. So, to sum up, one last smash cut so that we can summarize everything. So basically, we have 3 categories of angles associated with circles. Category 1. The vertex of the angles are inside the circle. So with this first circle here, that is a central angle. And in general, the central angle is equal to the measure of the intercepted arc. But I want to point out that what I'm about to show you with circle 2 also works with central angles. It's just kind of a dumb way to do it. With circle 2, the measure of angle 1 is equal to 1/2 of the measure of AB plus the measure of CD. Notice, if I look at this first circle, that also works because AB and CD are going to be the same size, and so I'm just taking half of something that I've doubled. So it's a dumb way to do it, but it does help see why these categories are the way they are. So if the circle has the vertex of an angle inside of it, you are finding half of the sum of 2 arcs. Now, what if the vertex is on the circle? So in these cases, I've got the measure of angle 2. Well, this is going to be 1/2 of the inscribed arc or the intercepted arc. So in this case, for both of these, it's going to be 1/2 of that XY. So that works here. It also works there. Finally, we have the angles that are formed when the vertex is outside the circle. So in this case, the measure of angle 3 is always going to be 1/2 the difference of the intercepted arc, which looks like this for this circle here, which is, I guess, circle number 5. So the measure of angle 3 equals 1/2 of the measure of FG minus the measure of DE. Here, it's going to be the measure of angle 3. So this is circle 6. The measure of angle 3 is going to be 1/2 the measure of FE minus the measure of arc DE. And then finally, with the last circle, circle 7, the measure of angle 3 is going to be 1/2 the measure of the major arc of DE. That's the major arc, minus the measure of the minor arc of DE.